exact sequence can lead to very different energetics, and there's some sequences of amino acids that would have a distribution of energies that would correspond to more what we'd expect for protein folding. So remember in the example that we did, we had one sequence where all the compact structures were the same energy, so 7 epsilon. In the other one, there was one that was 2 epsilon, whereas the others were 4 epsilon. Okay? So we're going to now build on some of those ideas and spend a bit of time talking about some experiments that have been done in the field of protein folding. The one really important experiment that you should be aware of is by a guy called Anfinsen. So this is an experiment, a series of experiments that were done in the 1950s. And one of the hypotheses that Anfinsen had and other people in the field had was that basically, as you know, the protein has 3 types of structure, or 3 types of hierarchy, of actually 4 types. There's the primary sequence of amino acids. Then I have secondary structure. Then I have tertiary structure. Then I have quaternary structure. And one of the hypotheses that Anfinsen had was that basically all I need to have is the primary sequence of the amino acids in order to fold my protein. So all the information needed to take the system from a primary sequence, okay, to this guy here on the right is all encoded in the information of the chemistry of the amino acids. So you don't need anything else for protein folding to happen. So this was the hypothesis. So primary sequence determines native structure. Primary sequence determines native structure. Okay, so that was his hypothesis, and so he did a set of experiments to try and validate this. So let me just try and walk you through what he did. Okay, so he took a protein. Okay, don't worry about what this protein is. It's just some protein which has a 3-dimensional structure. This protein also has disulfide bonds, sulfur-sulfur bonds. Okay, so remember we discussed this. These are the strong interactions, they're covalent-like, that are found in bacteria that live in hot vents. Okay, so this is a protein, it has sulfur-sulfur bonds, and what he did was, he did 2 things. He added this chemical called 2-mercaptoethanol. It's not detailed, not important to know what it is. You can call it 2-ME. What 2-ME does is it reduces these covalent bonds. By reducing means it adds hydrogen to the sulfurs. So it breaks these covalent bonds. Okay? And the other thing that he added was urea. So urea is a molecule. Maybe I'll go ahead because this is important because it's going to come back. Here we go. Urea looks like this. Okay? It has an NH2, NH2, and a CO. So this should not be a surprise to you. This is the amide backbone in proteins. Okay? This group. Okay, so this is how urea looks. And so urea is known, let's go back. So urea is known to be a denaturant. So urea denatures proteins. What does that mean? If I have a folded protein like this, and I put urea, it becomes unfolded. It changes the secondary structure. It changes the conformation of the protein, so it denatures it. Okay, that's what urea does. 2-ME takes, so this is 2-mercapto ethanol. It's not important what that is actually. It takes sulfur-sulfur bonds and makes them like that. Okay? So that's what this chemical does. And so what he did was he added 2 mercaptoethanol and urea to this protein, and then he measured the activity, the function of this protein. Okay, so this protein has a particular function. The details of its function are not important. So like, as we've discussed in the previous lectures, all proteins have a particular function. So biologists have a way to measure whether this protein is functioning or not. So he added these 2 things and he tried to measure the function of this, and it only worked with less than 10% efficiency. Here it worked with 100% efficiency. Here the efficiency dropped significantly after adding these 2 molecules. Okay, it's known that this first guy, 2 mercaptoethanol, it's a reducing agent, so it causes this chemical reaction, and it's known that urea causes the protein to unfold. Okay, so the picture that emerges from that is that the protein now looks like this. It's unfolded, and it has all these sulfur groups now have hydrogens on them. Okay, so now when he measures the function of the protein, it doesn't work. The efficiency is dropped. Okay. Then he tries to repeat the process, but reverse it. He removes urea, and he removes 2 mercaptoethanol. And when he does that, it goes back to its 100% efficiency. Okay? So what is this telling you? This is telling you that essentially all the information of the functioning or the 3-dimensional structure of the protein is encoded in simply the primary sequence, because when I can put these 2 molecules, denature, and change the chemistry of the sulfur groups, and I can create an unfolded protein, but when I remove them, it goes back reversibly to exactly the same efficiency. Okay, so is this first part clear? If there are questions, please ask. Yeah, please.
Which efficiency of the protein?
The efficiency of a protein. So let's say a protein has to catalyze a particular reaction. Okay, that reaction we can associate an efficiency associated with it. Okay, so it's just a number that allows us to see how optimal the reaction is. Okay, so now he does 2 things. Now he says, let's remove the 2 mercaptoethanol. Let's remove this guy, but keep urea. So let's remove this and leave this. So if I remove this reducing agent, you oxidize those SH bonds, and so you reform sulfur-sulfur bonds. But the protein remains unfolded, because that's what urea does. Urea, it keeps it unfolded. But what's interesting here is he measures the activity, the efficiency of this protein, and it's only 30%. It's not the same as this one. So what's happened here? Essentially, by keeping the protein unfolded, okay, with the urea, by introducing this chemical, the wrong sulfur-sulfur covalent bonds will form. So you see now there's a sulfur-sulfur bond that formed between 2 parts of the polymer that weren't in the original one. So this is an unfolded protein with sulfur-sulfur covalent interactions, but in the wrong conformation. And then, after he removes the urea from this, it goes back and regains its full activity. Okay, so what is this telling you? Well, what it's telling you is that there are very specific interactions within the polymer that are needed to get the right functioning of the protein. So even if you form sulfur-sulfur bonds between parts of the polymer that are incorrect, that doesn't mean that you will get the optimal efficiency of the protein. Okay, so it's a very finely tuned and delicate process, protein folding, and getting all the interactions between the different parts of the polymer. Okay, so you need specific sulfur-sulfur interactions, not just a random sulfur-sulfur. You need specific sulfur-sulfur bonds in order to get the optimal efficiency of the protein and the optimal native structure of the protein. Okay? So is this clear? Okay. So these were sort of very interesting experiments because it really showed that you, for the most part, you need all the information to reversibly fold and unfold the protein is contained in the primary sequence. Okay, and the order in which amino acids appear in the primary sequence will sensitively affect the eventual three-dimensional structure that the protein takes. Okay, so, and this is actually sort of well known, which is that if you were to take thousands and thousands of proteins and look at what is the probability of finding a specific amino acid in a helical structure, or a beta sheet, or a turn, you will find that some amino acids have a certain propensity to be more in helical conformations, others in beta sheet, and also groups of amino acids. So if there's a particular group or sequence of amino acids that appear in the primary sequence, they're more likely to have different tendencies to fold into different secondary structures. Okay. So, well, how does, if the protein folding process is not random, how does the free energy landscape of the protein look like? Okay, and so this is still a topic of research in the field. So the simplest model is to think of, the standard physicist approach is to say, I have a two-state model. Folded, unfolded. Again, there have been lots of simple models built on this idea that the protein folding process is simply going from an unfolded state to a folded state. And I have to go through essentially one rate limiting step, one barrier, one slow process, which will be dictated by this barrier height here that will drive the folding. It turns out that this is not true. Okay, it's not true because the free energy landscape of protein folding is much more complicated. And it's much more complicated because there are lots and lots and lots of intermediate states, okay, with barriers that are not insignificant. Again, so the free energy landscape of protein folding is a very rough free energy landscape. So it's characterized by lots of intermediates, lots of minima in between. And the classical picture is that it has this funnel-like free energy landscape. And this funnel-like free energy landscape is what prevents it from being random. Okay, so you have the funnel describes going from a region where things are entropically favored. So right here at the top. And then entropy of the protein is going to reduce, but then you start gaining on enthalpy. The two, remember, more or less compensate each other so that the magnitude of this free energy is not so large. Okay? And you go through lots of these intermediate states until you get to the native structure here at the bottom. So for those of you who might be familiar with glassy systems, so glassy free energy landscapes. In glassy systems, this is also what you typically see. Okay, so glassy systems are characterized by regions with very deep free energy minima. Okay, so this is the funnel-like free energy landscape, which makes it not random. Now, does protein folding happen independent of, let's say, other competitors or other things in the cell? No. There are other facilitators, other proteins that may also help protein folding. Okay, so it's not that a protein folds on its own. There are also other molecules, other proteins that may help and guide the protein from moving in different directions, which I'm going to tell you about shortly. Okay, so is this clear? Okay, so this more or less this again summarizes what I was telling you about. So if this energy here, this energy is between how much? 5 to 10 kBT. This one. Okay, so all these other intermediate states are much smaller than that. So what does this mean? This means that the protein free energy landscape involves a lot of soft modes, soft degrees of freedom. Okay, so it's not like what you might be used to think about in solids. In solids, you know, I have one deep minima, harmonic approximation works very well. Here, you're dealing with highly anharmonic systems with lots of free energy minima. Okay, and it's the fluctuations of the protein in these minima that essentially drives the dynamics of the system. Okay. Okay. So there's a very, very, very subtle balance of internal energy or enthalpy and entropy in this process. Now, you should be aware that this is a projection in one dimension of many degrees of freedom. So I am looking along one coordinate here. This is not how it actually is. In reality, you can't even, so you can only visualize this in 2 or 3D, but in reality you have a very rough free energy landscape in some high dimensional manifold, and you have to think about this protein hopping between lots of different pathways, eventually reaching the ground state or the free energy minimum of your system. And along all these processes, along all these hopping events, it involves a delicate balance of enthalpic interactions between the protein-protein, protein-water, water-water, and then of course the entropic degrees of freedom of the protein and the water. Okay?
Excuse me.
Yeah, please.
In this case, actually in the previous one you
Yeah.
said, this is the projection, so along the x-axis, it's a configuration.
It's some effective configurations. Yeah.
So, is this symmetry also reflected to the original one, because there seems to be two classes, all the configuration can be divided into two, such that from this class there is a certain energy which matches from this one. So it's
you mean yeah,
like reflective symmetry. Yeah.
in the way it's drawn here, yes, and because of the way if you can choose a configurational coordinate where what you're saying is true. Okay, but it's not always the case.
So if we go in a two-dimensional case, it will be a circle.
Exactly.
A dome.
Exactly. A cone.
Cone.
A cone. It will be a
There
cone.
will be on the configuration line, the circle will have same energy.
That's right. Exactly.
So
That's
will
right.
this keep growing and growing in higher
Boo.
dimension? This kind of.
I don't know the answer to that. My feeling is no. That these systems are, as you go to higher dimension, you will not see this type of symmetry happening. So let me try and think of an example.
Because what I was saying was, since they are in the same energy here, energy points, their energy like in a circle, so there is high degeneration. For example, going from the point at the left,
Yes.
and from there to the other point at the right, same point, it
Yes.
doesn't take energy.
That's well, it doesn't take energy in.
They are in the same energy line. So
Yeah.
from a higher state, it can either go there or there.
So okay, if you think of it in terms of thermodynamics, yes, they have the same energy level. However, there's rates, there's a dynamics. So the rate, the transition state, to go from here to here. So in projected in this space, these two configurations look like they have the same energy, but in higher dimension they may not be. And my response to that is that because I don't know how exactly it's going to change in higher dimension, it's very difficult for me to say, yeah, what will happen exactly. Because so the way it's drawn here is that they are at the same energy, these two configurations, but this relies on integrating out all the other degrees of freedom. How exactly that will change if there are some underlying other slow degrees of freedom that are coupled to this. Let's say if you take, let's say this is Q1 and this is Q2, okay? The value of the configuration coordinate. Now let's imagine, orthogonal to this. At this value, I may have a barrier. At this value, I may not. This is an assumption one makes, and this is actually why these types of problems now are very interesting from the point of view of dimensionality reduction, data science, machine learning, all this stuff, because you're dealing with many particle systems, large degrees of freedom, and you want to know what is the correct way to project into low dimension, preserving all the relevant information. In these, these types of pictures came 20 years ago, when people weren't thinking about these types of questions and problems. So something I sort of I haven't described to you is this. There's this intermediate region known as molten globule states. So these are intermediate states which are not unfolded, they are not folded, they're in between. Okay? And the reason why they're important and interesting is the following. So here you see it, unfolded, folded, molten globule. So it has some secondary structure, but it's clearly different from this, but not quite the folded secondary structure. Why this is interesting and useful is because of a real biological problem. because what's been shown is that if your system sits here for a long time in the molten globule state, this can open up another pathway in another dimension, in another direction, which can lead to the aggregation of these species. Okay, so what you see here is that many of these molten globule, think of it as another state. So think of it as, so now I have, instead of folded and unfolded, I have folded, molten globule, unfolded. Okay, so if it gets trapped here long enough, this can open up another, so let me try and do this. So it can open up some other fluctuations in another direction that lead to something pathological. So you see here, what you find here is that this is now aggregating into something else. So this is a nucleation problem. I'm nucleating something bigger from this initial seed, and this is pathological. Okay, so it's good. This is not what you want, because then this can lead to all sorts of diseases and pathological things in the cell. Okay, so this is why this intermediate state is rather important. Okay, and if the system gets trapped here long enough, it can open up other pathways that you don't want to happen in the protein folding process. So this is seen, you can see it more clearly here. Okay, so this is the again, native folded structure, unfolded, and now I'm showing this in one dimension, but you shouldn't think of it as in one dimension. The thing aggregates into another free energy minima, which this will be much lower in energy. And of course, now we're talking about a system where the number of particles is also growing. Okay, so here it's one particle, one protein. Here it's many particles. Okay. Okay. Fine. So now let's since we want to understand what can we do to perturb the system to affect its folding character. That's what you want to do as a physicist. You want to add an electric field on, you want to put pressure on, you want to put temperature. Okay. So now we're going to shift the conversation to what we can do with that. And whether you know it or not, all of you have made eggs, I assume, in your life at some point. And when you make eggs, you're always doing some type of denaturation and chemistry to proteins. Okay? And so, well, what can you do to denature a protein? So you can heat it up, turn on temperature. When you turn on temperature, that's going to unfold. Okay? It turns out, actually, that you can also denature a protein by cooling it. So that's a bit counterintuitive, right? Usually, what I would have expected, if you cool a protein down, you will stabilize it even more. So that's a puzzle. How do you can denature a protein heating it up, and you can also denature a protein cooling it to below some temperature. Okay, so keep that at the back of your head, because we're going to come back to it. You can exert pressure. Okay, if you squeeze a protein, you can also denature it. And that's sort of easy to understand. When I squeeze a protein, or squeeze a protein with the bath around it, I'm basically pushing in water molecules into the protein. Okay? So it's like a sponge of some sort. You can think of a protein as a sponge. If I compress it, I'm going to put stuff in it. So those are the, let's say, temperature and pressure are the obvious things you can do to denature a protein. you can also denature proteins by pH. Okay, so I go to very acidic, very basic conditions, I can denature a protein. And this, okay, we can also pretty easily understand, because when I add protons or hydroxide ions to water, I change the charge, the protonation state of different amino acids. So I make them unstable. Okay, denaturants. So denaturants are like urea. So other chemicals. If I take a protein and I put other chemicals in the liquid around them, those chemicals will interact with the protein in a specific way and can denature them. Last one, if I take a protein and I put it near an interface. So, an interface. How can I describe an interface to you? Well, when you're cooking, for example, again, always going back to food, and you take a glass ball and you mix and you beat the protein, there'll be protein molecules that are sticking to the glass surface or plastic surface, and the proteins that are sticking to the glass will slightly change and can denature. So you can change the conformation. So there are many, many, many ways that you can do it. You can perturb your biological system and measure the response to see how it's affected by these properties. Now, in all these different things, all these different variables, all our conversations about enthalpy, entropy, protein, water, protein, all those things remain the same. So you have to keep that at the back of your head, that in order to try and rationalize and explain all these different effects, you need to have some understanding of how the enthalpy is changing and how the entropy is changing in all these processes. Okay? Yeah?
I'm rather failing to, okay, picture of pressure.
Yes.
You put there an egg and it looks more or less the same, like the one that has been affected by temperature.
That's a good thing, because that means that, well, it's not always this. So okay, don't take the picture too seriously. All this is trying to tell you is you can change the chemistry or the structure of your protein in the egg. When the chicken lays the egg, you have proteins in the egg, right? Okay. By heating it up, this is sort of interesting, right? Usually when you heat things, they don't become more solid. But when you heat up an egg, it solidifies, which is why it makes it tasty to eat. Well, why does it solidify? This is because of proteins aggregating together to form nice precipitates, and that's okay. So you can do that with heat, and you can also do that with pressure. Okay? So.
In general, what we are saying is, whatever it unfolds it.
Yeah.
So normally.
Not necessarily. Well.
Yeah, folded
Yeah.
must be a more dense structure. Unfolded must be a less dense structure.
That's correct.
From our perspective. But here it's the opposite.
In which? No, sorry.
In case of eggs.
Yeah. Sure. Indeed, because there are two steps. So you do this, and then it's many of these that collect together to form the precipitate. That's what makes the egg.
Okay, so we can say that when it's in a folded structure, there are more unused space in between.
Yes.
That, for example, and when it's unfolded,
Yes.
it's just like, okay, it may be just like modeled by a simple paper. So just scramble it,
Yeah.
just put it in a plane,
Yes.
and then stack it.
And then stack it.
Yeah.
Exactly. Good.
Is there a denaturing process that makes it more folded?
Is there a denaturing process that makes it more folded? Interesting question. Yes. If you go from, if you change the isotope of water, so you take hydrogen and you change it to its isotope, deuterium. Some people have shown that stabilizes the secondary structure more.
So does that mean that there's still another lower well in the free energy?
So, okay, good question. Remember, this is in a space of coordinates without the denaturant. Okay. Then, if I put in the denaturant, then this whole free energy landscape changes. So I can no longer really compare this one to that one. Because what's going to happen? So for example, I add in a denaturant, and then this evolves into that. Okay. If I add D2O, I change the isotope. Well, maybe this changes this free energy difference. So those are the things that I can meaningfully compare. Okay, so this is just let's say a qualitative picture of this. So let me try and show you how people have tried to think about this. But I have to say it's not complete and it's not completely understood. So there have been experiments trying to measure how the pressure, temperature, phase diagram of proteins look like. Okay? And what's come out of this is that the pressure, temperature, phase diagram of a protein has an elliptical shape. It looks like an ellipse. So that's an experimental observation. Why? This is the question. Okay, so this is your typical phase diagram. So inside this, I'm in my native structure, folded, and then outside of it is denatured. Okay, so people have been trying to think about how to rationalize why the pressure, temperature, phase diagram of proteins has this elliptical shape. Okay, so remind you again, if I heat, that means denatures, but also if I cool, it denatures. So this is weird. Why does that happen? Okay, so what I'm going to show you is actually a paper from, well, over a decade ago that tried to address this issue. And so I'm going to show you what they did, and then we'll have a discussion about it. So, okay. So what do we want to do? We want to look at the free energy difference between the folded and unfolded state as a function of temperature and pressure. That's the question. And so, well, what you can do is you can say, well, let's take the free energy difference and do a Taylor series expansion in T, the first derivative, second derivative, first derivative of P, second derivative of P, and then the cross term. Okay? So that's the starting point. And now I want to understand, can I relate these derivatives to something that I know from thermodynamics? Maxwell's relationships. Yes? Okay. So this is related to the change in the entropy. This one is related to specific heat, change in volume, compressibility, thermal expansivity. Okay, so these are all first derivatives, second derivatives, they're related to some thermodynamic quantities that I can try to make sense of. And the delta here, remember the delta is the change in the free energy, or the change in compressibility, or the change in the volume upon folding or unfolding. Yeah, that's what we're after. Okay, so yeah, please.
Is that phase diagram like universal for every protein?
Let's universal in the sense.
Because
Yeah. So what people, they've been on many proteins. Experiments show that or suggest that the phase diagram has this elliptical shape.
Because I've been trying to relate it to, for example, the protein found in eggs, you don't have that kind of reversibility. When you go to one, I don't expect, like, if you hit it and denature it to a certain kind of state, you don't expect to move back. Right? Because you have said that if you try to reduce the temperature, you denature, and if you go above the temperature, you still denature. So it's like, I don't know whether I'm asking.
No, once you go out of the ellipse, you can't come inside.
Yeah.
Do you mean that inside the ellipse we still have the protein?
Yes.
In the native state?
Yes. There's a certain range of temperatures and pressures at which the protein is folded. It remains in this minimum. Okay? Then, if I go outside of this temperature range, I shift the equilibrium so that now the free energy minima is, the free energy surface looks more like that. This one. So now, the unfolded state is the stable part of is the dominant conformation. But what I'm trying to tell you is that the temperature and pressure are knobs that you can use to change the shape of the free energy profile. Yeah.
Which order of temperature is necessary to denature the protein?
Say it again.
Which order?
To which 60, 70 degrees, roughly. It varies.
So if you act too much temperature, is there a possibility of destroying the protein?
Absolutely. Absolutely. And that's what you do. When you make eggs, that's what you do. When you heat up a protein, it denatures above some certain temperature. It changes its conformation, so you break all the interactions. You don't break covalent bonds, just to be clear. Okay, unless you go to insanely high temperature. But you break all the electrostatic interactions, hydrogen bonds, van der Waals, and so you create something that looks like this. And in the case of this example, you then have many of these that stick to each other to form a solid, a precipitate. Okay, so yeah, please.
So we have that phase diagram of on temperature and pressure.
Mm-hmm.
So you can you get the similar in the case of pH also?
In the case of?
pH.
Yeah. Good question.
Maybe it will be ellipsoid.
I don't know. I'm sure that there is a a pressure, temperature, pH phase diagram. Let me think actually. So I think that with pH it's more so if this was pH, I think that this is how it would look, so around 7, and then as you go to 1, you create unfolded 1 and unfolded 2, which may not be the same, which will not be the same, and this will be 14. So this is how I think it will look. Now, whether it's the shape of it will depend on the, let's say, the curvature of this left and right side, and then how it looks like in temperature and pressure as well. Don't know. I'm not sure anyone knows actually. It's a good question. But along pH, this is what you'd expect.
That minima does always be in the pH 7 or?
Close to pH 7. I mean, you may have a minima at 5 or 7, but for sure when you go to the extreme, you're going to push the equilibrium to unfold it, because now you have a lot of either positive charge that needs to be stabilized and it can't be, and here negative charge that needs to be stabilized but it can't be. You can, if you introduce ions, so there's another thing I didn't add to this is ions can also affect the phase diagram. So if I introduce ions into this, then I can stabilize the low pH or high pH. Counter ions to make it neutral. Okay, so there we are. So in principle, these are things you can maybe measure from an experiment, okay? But at least these are quantities that we can try to think about and try to make some reasonable guesses on how they change when a protein folds or unfolds. So okay, so if I put those things, those thermodynamic quantities into that Taylor series expansion, that's what I get. So I'm taking this picture from that paper, and so if you want to think of it like this, you have this parabola, where a two-dimensional parabola. What we're looking at is a projection of it in temperature and pressure, and the y-axis here is the free energy. Okay, and so we wanted to see when the free energy is 0, when the two are at equilibrium, when delta G between the folded and unfolded is 0. This is essentially this is the projection of that on the temperature and pressure plane. Okay, so now I have these quantities. What can I do with that? What will allow me to say whether I have an ellipse or not?
Excuse me.
Yeah.
In that case, it's like pressure and temperature here, and there is this thing. So if we cross it, it will be a ellipse. So inside that ellipse,
How do you?
we are just at the boundary of the ellipse.
So it's drawn here as an ellipse.
No, but the condition will be satisfied just at the boundary, not inside.
Yeah, I agree. But that's what I want. I want to look at the conditions of the boundary. So, I want to look at where delta G equals 0, because below that it's negative. Delta G is negative.
No, because in the previous picture,
Yes.
it says that all the region inside the ellipse is also native, but the condition is satisfied only at the boundary, or is it negative inside?
So sorry, is what
For
negative?
example, let's say if this is my certain
Yes.
thing and here is temperature and P,
Yeah,
we want to extract only the condition for G equals to 0.
that's
So
correct.
if we cut a dome with a
Yeah,
plane of paper for G equal to 0,
yeah.
it will be the ellipse and the condition will be satisfied only at the rim of that ellipse.
Well,
So the projection,
so no, this is just okay. This is just to simplify the calculation. I can take a cut. I can take similar cuts at all points less than 0.
okay,
Yeah, I mean so the reason we do that is just so that I can set this guy to 0 instead of something else. But
0 or less.
listen, you can, without loss of generality, you can do what you're saying.
So it is negative G axis.
Yeah,
Okay.
yeah. Well, here it's shown as the negative.
That's
Yeah,
right.
exactly. Here it's shown as the negative. But so now, what can I do with this to infer if I have a hyperbola, a hyperbole, or an ellipse? How do I prove that I have what conditions does this have to satisfy, these variables, in order for this thing to be an ellipse?
P minus P naught squared. We know coefficients.
There's a relationship of the, that's right. So there's if you take an expansion of AT squared plus BP squared plus 2A, 2CD, T, P, there are certain conditions of the coefficient which it has to satisfy so that it's an ellipse. C squared is
X
over
squared.
2AB is less than 1. Okay?
Or maybe we can, for ellipse, there is a simple check. We can just say pi AB equals to the area of the ellipse. So if it can be plotted, we can just multiply it.
Yeah,
and
say
see.
that again. Pi AB.
Area of the ellipse is pi AB.
Yes.
Same with the
Ah.
axis. Simple check.
Yes. Yeah, I didn't think of that. Okay. So, now, actually, it would be interesting to see if you come up with the same thing. But
I don't think that will happen because it's a little shifted one. It's not the center is not at the center of the ellipse. The
right.
would be at the
Right. So, yeah. Okay, so if you do the math, this is what you get. This is the C squared 2AB less than 1. That's where this comes from. So this is the condition for an ellipse. And what this means is that the change in thermal expansivity, the product of the change in thermal expansivity, times the change in the heat capacity upon protein folding has to be greater than 0. That's what the experiment said. If doing this Taylor series expansion up to second order is correct, and if I have an ellipse, this condition must hold. Okay. Now you have to come up with arguments to rationalize and explain why this product has to be greater than 0. So I'll tell you what they say, although I'm not entirely convinced about it. So this says that the heat capacity upon protein folding has to be greater than 0. The heat capacity of what? It's the heat capacity of the protein and the bath surrounding it. So this says that the heat capacity of the denatured protein has to be greater than the heat capacity of the folded protein. Why? Well, let's try and find where this is. Yes, okay. Okay, at ambient pressure, a positive was measured for all proteins, investigated blah. Okay, unfolding of a protein brings the hydrophobic amino acid in contact with water, which forms an ordered structure around these amino acids, the so-called iceberg. characterized by rather well-ordered hydrogen bonds. It is the extra energy needed for melting the iceberg which causes the higher specific heat capacity in the denatured form. Does that sound reasonable to you? It doesn't to me. So what are they saying? They're saying that hydrophobic, 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 HP, HP, HP. So unfolded, folded. So they're saying when I have all these hydrophobic groups exposed, the bath here is more ice-like. It's more ordered. Here it's less ordered. So the energy required to melt, to destroy the structure of water on here is more than it is there. Not so obvious to me.
I don't know, I just got something, I'm not very clear about
Yeah, please.
I think similar thing also happened in water below 4 degrees centigrade. It's called the anomalous behavior. So
Sure, there's a density maximum at 4 degrees.
So I think it also has to do with some specific heat capacity.
So there's the heat capacity of water has a minimum much below 4 degrees Celsius. So you're talking about if you look at the specific heat capacity of water, there's a minimum in super cold region. I think it's about 230 Kelvin. It's much lower in temperature. So you're right, there are these anomalies, but the problem with this type of argument is that it neglects the fluctuations of the environment, and it has a picture that assumes only non-polar or hydrophobic interactions with the solvent. Whereas, well, we know now that things are all mixed and entangled. So it's not so clear that this statement is actually true. So, okay, at least I'm not convinced. So I'm sort of also saying this here because I'm making this as a proposal to someone to give a short talk on the last day for 10 minutes to come up with a convincing argument. Or maybe a non-convincing argument is fine too. If you convince yourself as well, this is a non-convincing argument, even better. So, and what's the other one? So the other one is, the compressibility. So the compressibility of the denatured state is higher than the native one. This I can understand, because the compressibility is related to the volume fluctuations. I can rationalize that in my unfolded state I have much more conformational entropy. I'm occupying more volume, and also there are larger volume fluctuations. But this one, not convinced. Okay, so anyway, let me know if you want to talk 10 minutes about this. All right, so
but this is something that is true.
It is. It's true.
Argument is
Exactly. This is the point. This is why it bothers me, is because it's a fact. Well, it's an experimental fact that it's an ellipse. And now you could argue: is this sufficient? probably it's okay. Okay, so there must be some truth to this. There must be there is truth to this. It's the point is that the explanation is wrong, or the explanation doesn't make sense. And then maybe there is a more a better explanation for this. Okay, so I would say that's at least from the physics world, the temperature, pressure, phase diagram of proteins is something that people are still thinking about and still don't have a complete understanding, especially going to the cold temperature regime. Because when you cool down a protein, you can unfold the protein. And this is interesting. And it's not clear exactly. The mechanism is not exactly clear. Okay? Okay, so pressure, temperature, chemical denaturants. So this is urea. Okay? Urea is a molecule that looks like this. It has NH2, NH2, and a CO. Now, this should be very familiar to you because it's the backbone of the peptide. Sort of. Okay, so there's, you don't have this. And you don't have this. But you see that the peptide backbone has this group. Right? All proteins have this. Now, what has been shown in numerous experiments, numerous simulations, is that when you introduce urea into a liquid, it denatures the protein. And the question is why? Why does urea denature proteins? And well, there are two possible things you could suggest. One is that the urea makes strong interactions, electrostatic interactions, dipole interactions with the peptide backbone, and when it does that, it causes the protein to unfold. The other thing you could say is, well, or in addition to that, the urea interacts with the solvent in a way that causes the protein to unfold. Okay, because when you introduce urea in the solvent, in the liquid, it's also going to form strong interactions with the solvent, and maybe that couples to somehow reducing the stability of the protein. Okay, so there are many people who've been interested in focusing on trying to understand how urea and other denaturants denature proteins. So I just show this to you as a simulation. So these are molecular dynamic simulations of a protein. That's the crystal structure. This is the structure of the protein in 60 degrees Celsius. Then in water at 125 over time. And you see that at 125 you begin to see that it's beginning to denature. It's losing its secondary structure. Then they do another experiment where they put urea, so 8 molar of urea in these 3 simulations at 60 degrees, and over time you see that the protein is denaturing. Okay, so this is just one example of many that show that urea is in fact a denaturant and unfolds proteins. How do you think you could measure this experimentally? Experimentally.
You said you could measure the function.
Okay. that's the easy answer. So what physical measurement could you design to prove this? What would change in what you know about maybe electronic properties? What physical processes would change as you go from a folded to an unfolded protein?
In eggs, density will change.
Okay, so you could measure things like structure factors from neutron scattering. Okay, structure factors will tell you about density fluctuations. So yes, okay, that's one way. Okay, you can measure function. So if you're a biologist, you can come up with some assays, and that will tell you what the efficiency of my function is. Yeah, that's another way. Another way is optics, optical properties. So you can measure absorption spectrum. So many proteins absorb energies at only particular frequencies, particular wavelengths. And these are optical excitations, so exciting electrons. And the typical frequencies that proteins absorb at about 280 nanometers. Okay? So this is in the UV range. And if you try to optically excite a protein that looks like this versus like this, the energies at which you'll be able to excite will be different. So optical excitations can be used to interrogate conformational changes in proteins. Now, these are extremely, extremely messy systems. And this is why they're interesting, and also, well, sometimes people try to avoid them. Because you're dealing with very soft systems with lots of fluctuations, lots of different conformations, and small changes in the conformation can change, let's say, the types of optical excitations that you have. Okay, but in principle, that's a technique that can be used to study the folding of or unfolding of a protein. That's exactly what I'm saying here. Okay, let's skip this. I think we'll skip this and go straight to. Yeah, maybe I'll end this free energy discussion on the following note. So I've only shown you, presented to you a picture of the funnel free energy landscape. And I've said, well, this is how free energy landscapes of proteins look like. Well, this is true, but not always. And so there are a whole class of other proteins known as intrinsically disordered proteins, where the free energy landscape is not characterized by one deep funnel, but it's a flat free energy landscape with lots of different minima, and all of them are equally likely. Okay. Now, the reason, I'll just end with this, the reason why physicists are very interested in this is because getting these coordinates, getting the right dimensionality, getting the right degrees of freedom to characterize the thermodynamics and the kinetics, the dynamics associated with these problems is a very interesting physics problem. Okay? And so that's why there's a lot of interest in trying to come up with methods and tools and algorithms that will allow you to construct and develop these types of pictures. Okay, good. So, are there any questions on the protein folding part before I switch into, let's say, another topic? Please.
How were they able to experimentally probe the shape of the free energies for the protein folding?
They can't. So, this is, well, okay, not exactly. So, if you are, there's some experiments who are able to do single molecule experiments. So they take a single molecule, they isolate it in solution, and they're able to, for example, So that's your protein. You put a tag that emits light, it fluoresces. Okay? And then you, let's say you have another tag here. So let's call it donor and acceptor. And as this protein is breathing in solution, when these two guys come close to each other, there's certain physical processes that happen, like for example, energy transfer or electron transfer. If that happens, then you can say, I can monitor how the optical properties of this thing changes when it goes from DA to something like that. But it's very delicate and complicated. So in reality, the free energy landscapes is something that lives in the theory world. But you are able to compare, differences and rates. So those are things that experiments can measure and can predict. And then theory can come in and try to also predict those values, but then complement the analysis with more details about how the pathways. The pathways are basically very difficult to do experimentally. So, yes.
From this picture, it seems that we know quite a lot about this protein folding problem.
Yes.
So
Yes.
what is still the missing information so that we can say that we know, we have completely solved the problem?
There are two things. One is, one is more of it's a theoretical problem, but it's a theoretical problem that it's a language that needs to be given to the biologists. And that's the following. That we assume when we write out when we draw these pictures, or when we come up with models for these types of processes, that the system lies on some low-dimensional manifold, 1 or 2 degrees of freedom. The reality is that there may be 15, 16, 20 degrees of freedom that are important to characterize the fluctuations of the system. So one question is, what are those 16 degrees of freedom? Okay, this is not known. Secondly, how do those 16 degrees of freedom couple with the bath? So typically in all these types of pictures, the bath is integrated out. It's thrown away. But in reality, you have a bath that strongly couples to these degrees of freedom, and you have a bath that also involves high concentrations of other molecules, 10 to the 6 proteins, 10 to the 10 ions. All these things are going to change the way the free energy landscape looks like. So I'd say that's one of the big challenges there from the theory side. The other side is more, I'd say, numerical and algorithmic, which is people know more or less how to fold a protein in isolation. Okay? Now the next question is, well, if I have a protein in a cell, how do I realistically account for the entire cell and all the gradients in maybe temperature, in concentration, and how do you account for non-equilibrium effects and how those change these types of processes? That's, I think, something that's not understood at all.
In a single word, what is the protein folding process?
You tell me. What do you think it is? So just use the words to help you. So you know what a protein is?
Yeah.
You are a protein. What? You're made up of lots of proteins. Okay, folding.
find, rather than most of the folding is to find a stable configuration.
Yes?
But what I'm asking is in terms like in the last lecture we said it was not a random search.
Yes.
So it was
It's
a
not.
random process.
It's not a random process.
So it's not a random process.
It's a directed process.
Directed process.
It's a directed process happening on a free energy landscape. So let me draw let's do this. Let me draw two pictures for you. So you'll see. Oops. This is scenario 1, and let me draw scenario 2. So, this is as best I can show you using some simple pictures where I have lots of local minima of the protein. There's one that's a very deep one. This is the folded guy. In the random search, I do a random Brownian walk, sampling all these states with equal probability. Okay? And eventually, I stumble on this one. Okay, random. Random in a potential that looks like this. Directed, I have a free energy landscape which is made up of lots of local minima, but has this a deep funnel, so that the system is guided to move towards this deep local minimum. And so it's very difficult for it to spend time outside in the entropic flat basin. Once it gets to some regime, it's quickly funneled down. So this is the difference. And so for these intrinsically disordered proteins, they look like this, without this. So this would take the lifetime of the universe for your protein to find your folded structure. But we know that it takes microseconds, milliseconds, for this to happen. Okay? Okay, so let me let's see. Well, I'll just introduce it now, and then we'll repeat it again on Thursday. So we're going to spend now a lot of time talking about equilibrium constants. We've talked about them already. Equilibrium constants between folded and unfolded. Okay, I've been telling you about free energy differences. Okay, and we now want to put some more meat on it. And so, because in general this comes up everywhere. I have an equilibrium between two states. Two molecules react together, they form another molecule, there's some equilibrium between them. And the equilibrium constant is the ratio of the concentration of this species to the product of these two species. Okay? The equilibrium constant is something that is experimentally measurable. And this is what experimentalists can measure. Experimentalists can measure this guy here. You may often see it written as a dissociation constant, which is just the inverse of this guy. Okay? Now, you'll see shortly that this equilibrium constant is essentially, it's what the chemists usually like to write it as concentrations, but the physicists often think of it in terms of probabilities, and therefore ratio of partition functions. Okay, this is where, and so this is related to free energy differences. So this is just a reminder. So let's imagine a molecule that can interconvert between two states A and B. Okay, and so I have one molecule, and I want to write out the total partition function of the single molecule. Well, all I need to do is to sum up of e to the minus beta Ej, states of A, states of B. So QA plus QB. Now, if I have n of those molecules, and I invoke the Boltzmann approximation, the total partition function of n particles, constant volume and temperature, is given by this binomial type expansion. Okay? Now I want to ask, what is the probability of finding amongst n particles those that are in state A versus those that are in state B? Okay, so the probability of finding Na molecules in state A is just a constrained partition function, a partition function consisting of Na molecules and B molecules divided by the total partition function. So then what you can do, okay, so it's easier to write it as the log natural of it, so the log natural of this probability, and I want to know what is the most likely occurrence of finding Na. And so all I need to do is to take the derivative of this log natural with respect to Na, set it to 0, and when you do all that, this is what you get. You get that the ratio of Na to Nb is just the ratio of the partition functions. Okay, this Na to Nb is the concentrations. Okay, of course, there's no AB here, but this is A going to B. Okay, but so these are all in different communities, different languages, they call them different things. But essentially, in physics, we are often interested in the ratio of partition functions because this gives me the free energy, the Helmholtz free energy difference. And this is why there's a lot of effort and interest in coming up with smart ways. So this also is related to your question. People are interested in coming up with smart ways of trying to estimate this ratio. So for very complicated systems like proteins, getting this ratio is highly non-trivial. Okay? Okay, so I think we'll stop here for today, and we'll continue with, so let me tell you where we're going to go. What we're going to do in the next class, and this is what you're going to work on in class with me, is we're going to again go back to a simple lattice model, like we did for the protein folding, but now we're going to consider a protein with ligands on a lattice, and we're going to ask what is the probability of finding a ligand in this site using the simple lattice model, and try to make some connection with this object here. Okay? Okie dokie. See you on Thursday. And then we're meeting on Friday again, Friday morning.